Hello everyone, my name is Đinh Tâm Nguyễn. I'm currently a cloud engineer in Viettel High Technology Industry Corporations and a master's student at Hanoi University of Science and Technology in Vietnam. I'm very glad to present my research named Enhancing CNF Performance for 5G Core Networks using SR-IOV in Kubernetes. The presentations will go as follows. First, I will introduce the problems that we aim to address. Then I will briefly talk about the previous efforts related to our research before discussing why our contribution is meaningful. The third and the fourth sections will describe our solution and the result we obtain with it. Finally, I will close my sections with some comment on future research directions. The first section is about the role of network performance in virtualization and why it matters in the context of 5G. First, we'll talk about the containers and Kubernetes. A container is a standard unit of software that packages up code and all its dependencies so the application runs quickly and reliably from one computing environment to another. Kubernetes is a container-based deployment platform with many benefits such as elasticity, durability, ease of management, and cost effectiveness. Cloud-native containerization is replacing virtual machine or VM as the preferred method of application deployment. However, the network requirements involved, including high performance and low latency, prove to be a barrier to deployment of 5G application. Cloud-native network function, or CNF, enable network functionality to run in containers instead of on traditional bare metal servers. The Cloud-Native Computing Foundation's CNCF Cloud-Native Survey takes a part of the community to gain a better understanding of where and how cloud-native technologies are being adopted. CNCF surveyed its extended community during May and June 2020 and received 1,324 responses. In 2020, 92% of the respondents say they use containers in production, an extraordinary 300% increase from just 23% in the first survey in March 2016. This is also up from 84% of respondents in 2019 and 73% in 2018. Again, we see steady growth in the number of containers that organizations run. Though using more than 5,000 containers hit 23% in 2020, up by 109% from the 11% we saw in 2016. 61% now use more than 250 containers, up from 57% in 2019. 91% of the respondents report using Kubernetes, 83% of them in production. This continued a steady increase from 78% last year and 58% in 2018. Of those using Kubernetes, 2 to 5 remain the most common numbers of production cluster, with 39% reporting that quantity, down from 43% last year. There was an increase in those who are using more than 11 production cluster, from 24% in 2019 to 28% in 2020, and a 56% increase from 2017. Following the same trend, the place of containerizations in 5G is inevitable and irrefutable. To leverage the cloud architectures, the 5G core relies on modularized and containerized cloud-native network functions, which enable high flexible scaling and functioning lifecycle management. Currently, 5G core production offered by Samsung are built on cloud-native, microservice-based technology. To get results, Samsung has actively cooperates with other partners and participates in organizations such as Cloud Native Computing Foundation or CNCF, which leads the de facto standard for cloud technology. They have also taken part in Open Network Automation Platform (ONAP), a techno-oriented open source project. 5G is set to cater both to a myriad of new services, such as AR, VR, mobile edge computing, and to traditional services such as voice, data, and SMS. An efficient charging system would be the bane of a network meant for an escalating number of transactions. Currently, we are using a real-time cost calculator called Virtual Online Charging System, or VOCS for short, to track telecommunications service usage. The current version, VOCS 3.0, is running on bare metal servers without enhancing network solutions such as Kali School and SR-IOV. In addition, other versions deploy the form of virtual machine in 2020s. VOCS DR work simultaneously with VOCS 3.0. The performance required of 5G has rendered our current bare metal deployment glaringly unfit. In fact, in the next version, VOCS 4.0 for 5G, go for a much-needed cloud migration. Network function virtualization (NFV) with single root input-output virtualizations (SR-IOV) has been documented to provide better network performance on VMs. Thanks to SR-IOV, multiple operating systems can share a physical interface via virtual functions (VFs) on the same network interface cards or NIC. SR-IOV enables network traffic to bypass the software weak layers of the Hyper-V virtualization stack. Because the VF is assigned to a VM, the network traffic flows directly between the VFs and VM. As a result, the I/O overhead in the software emulation layer is diminished and achieves network performance at nearly the same performance as in non-virtualized environments. Now I will quickly go over previous contributions made by other authors and how our research. Performance of different network models has attracted considerable interest in the realm of virtualization. Some research have investigated this topic specifically in the context of Kubernetes deployments. For instance, Kumer and Kubernetes in Study 4 note that Calico maintain adequate bandwidth for transmitting packets with low resource utilization. On research regarding SR-IOV, Jichang in Study 5 compared bandwidth utilization in latency experienced by VMs with SR-IOV, VMs with PCI pass-through, and content with PCI pass-through. Nevertheless, the article's comparisons left out containers with SR-IOV, and the authors did not comment on resource consumption. Study 6 indicated that SR-IOV have cut down virtualizations induced bandwidth loss by 2% and latency by 10% in VMS. We aim to emulate the success seen in VMs using NFV with RSIOV. We implemented SR-IOV in cloud-native networks intensive 5G applications. Our tests were undertaken within the charging function CNF, a module in was to be VOCS 4.0 for 5G. CNF is an apt candidate for the purpose of our research because it requires the lowest latency for a smooth running VOCS. Three metrics were considered: throughput in TPS transactions per second, latency in milliseconds, and CPU utilizations in percent. Our solution using SR-IOV and CPU pinning has boosted in the network throughput by 30% in comparison with the Calico-enabled Kubernetes deployment. In the next sections, I will give you an overview of the network models we consider in our research. We implemented the CNF with three major network models: bare metal, Calico, and SR-IOV. Now I will present the first two models and the SR-IOV models in the next slide. In the bare metal model, all the components of VOCs run on the same operating system, sharing physical resources like CPU, IAM, and network. This model does not suffer from the extra overheads caused by virtualization. However, heavy workload and frozen application can impact the system as a whole, leading to degradation in the quality of service. Calico is Common Container Network Interface, CNI. So what is CNI? Kubernetes offers the option to integrate different network solutions to CNI plugins. A CNI plugin inserts a network interface into the container's network namespace. It also makes necessary changes to the network configuration on the host. The plugin also assigns an IP address to the interface and setup roles that are consistent with the IP address management section. It does so by invoking the appropriate IP address management IPAM plugin. Casio creates overlay networks and establish connection between ports across the node, but it also manages network security and administration. The Calico node agent consists of two main components, Felix and Bird. Felix runs on machines that host endpoints and ensure that only valid traffic crosses endpoints by programming roles and if table on the host. Bird is a BGP border-gate protocol daemon that distributes roles routing information to other nodes. Calico supports three roles models: native, IP in IP, and VXLAN. The network model using Calico applies the IP in IP encapsulation tied only to traffic crossing a subnet boundary. The rationale behind using Casio in our test bed was that it offers a satisfactory bandwidth while not prone to resource exhaustion. Similar to virtual machine, containers on each worker nodes are sharing a virtualized single port of the NIC via software emulation. Figure 9b shows the containers-based network models, with the containers to network port connecting to NIC via CIN and container network plugin. The multiple layers of illumination predictably worsen container overhead. Furthermore, sourcing network traffic is a burden to the CPU, taking up computing resources meant for other applications. SR-IOV enables physical network functions to be shared without software emulation. It provides two function types, the physical function and virtual functions. The physical functions, a PCI function of a SR-IOV compatible NIC, configures and manages the SR-IOV functionalities, such as enable virtualization and exposing virtual functions, directly accessible to operating system. Other virtual functions represent a virtualized instance of the NIC and has its own PCI configuration space. Virtual functions share physical resources on the NIC with others and with the physical function. Thanks to SR-IOV, the container can directly send and receive packets to or from virtual functions in the user space instead of the current space. Taking CNIs out of the equations also removes the associated computing costs and latency. The charging function CNF, a crucial module of 5G core, encompasses support for both prepaid and postpaid billing within the same charging system. Our TED focused on the performance of the CNF, and the CNF had three layers: connectivity, stateless sets of components that interface with external entities via an API gateway, and business logics, a stateless set of application layers that include business logic, policy engine, and other necessary services. Data management, the data asset layer handling multiple backend storage, such as database. This is the deployment architecture for the C8Fs in VOCS 4.0, and also the testbed model we use. It consists of three main components: connectivity layers, load balancers, an external facing physical load balancer that receives traffic from other 5G service, CGW, a gateway that receives incoming traffic via load balancer, then converts it into a user format. Business logics, OCP, a component that handles calculation tasks. And data management, ABM, a process that processes queries into database, and database to aspire active database clusters, it containing information of 10 million subscribers. Next, I will talk about another important component, the microservice chassis libraries. Kubernetes implements the decoupling architectures in which services are separated from each other. The connection between them are established via service discoveries as well as an internal domain name system, DNS. These network interactions contribute to longer request and response times, as well as a higher latency overall. A service of load balancer type is attached to an ingress controller, a set of ingress that define where to forward traffic. Each traffic to a service containers that pass through an ingress controller may aggravate the container's network connectivity overhead. The microservice chassis libraries alleviate the issue as it lets applications discover the address of service containers and connect to them directly. The chassis accommodate scaling by updating the set of container address. As a result, network latency should be adequately lessened for a telecommunication application. Besides, we also apply another technology as CPU pinning to improve the performance of network models. So what is CPU pinning? CPU pinning scheduling algorithm in operating system usually elect a process to use the CPU at a given time, while the other processes are put in hold. The wait time can accumulate into discernible latency when the operating system has to handle many processes, including application process or containers. In the case of heavy workloads, the operating system's native CPU scheduling may jeopardize the performance of 5G core, which processes may have their resource temporarily taken away. To fix this problem, the CPU pinning can use to manually assign a fixed set of CPU cores to a process or a container. The process or containers then own a fixed number of these CPUs for its whole life cycle and no longer has to wait for others. Eliminated wait time is of course conducive to enhance performance. As you can see, every port or service in this test-based model uses 2 vCPU and 6 GB RAM. In this section, I will describe the simulation environment and our test result. We implemented the CNF with 4 different network models. The bare metal models, CPU pinning not applied. The bare metal model, CPU pinning applied. The evaluation baseline. The cloud native models using Calico, CPU pinning applied. And the cloud native model using SR-IOV, CPU pinning applied. All implementations of the CNF follow the same deployment architectures as shown in Figure 11. The test client generated the charging traffic to the CNF Network's Charging Gateway (RCGW) ports. The traffic includes both balance inquiries and a mixture of initiate, update, and terminate changing operation across data, void, as well as messaging service. Containers will run on 3 physical nodes with Intel 8260, which have a 96 2.4 GHz thresh and 256 GB RAM. Export used to vCPU and 6 GB AIM. Horizontal port autoscalers was used during the entire test. The Kubernetes version was 1.18 and the AirSpy version was 4.13 in all deployments. 20 million CPU accounts were provisioned over 6 AirSpy nodes. 3 metrics were considered: throughput in TPS, transaction per second, latency in milliseconds, and CPU utilization in percent. Result uses and system performance among different network models are listed here. The results show that CPU pinning compounded the CPU workloads. In both the bare metal models and the cloud-native model using SR-IOV, CPU utilizations reached 46% and 45% respectively. Meanwhile, the 2 remaining models were slightly more resource conscious, approaching approximately 40% in CPU utilization. The results also confirm the synergy between the CPU pinning and SR-IOV. In fact, the cloud-native model using SR-IOV and CPU pinning achieved 70,000 TPS, 1.5 times the TPS obtained by the bare metal model without CPU pinning, which was only 50,000 TPS. Therefore, this model may have VOCs serves significantly more customers. Interestingly, the latency does not go up, but rather drop to 2.87 ms. That said, the difference in latency among the 4 models were negligible. I will now proceed to the end of my presentation by discussing some potential future work. Our test results had demonstrated that model using SR-IOV and CPU pinning outperformed the bare metal models with CPU pinning by 30% in terms of networks, throughput, and packet processing. On the other hand, the cloud-native model using Calico performed worse than the bare metal model with CPU pinning, while the bare metal model without CPU pinning performed the worst. The subpar performance of the model using Calico can be explained by the need for more hardware resource as well as more time to encapsulate packets and route them to network cards. Meanwhile, SR-IOV had containers directly connected to NIC. Packets therefore bypass the current stack in order to deliver high performance. The optimistic results inform our decision to employ SR-IOV and CPU pinning in the production deployments of VOCs 4.0. Besides SR-IOV, DPDK is gaining traction as a means to improve computing efficiency and packet throughput. DPDK consists of libraries to accelerate packet processing by offload TCP packet processing from the operating system kernel to process running in the user space. The capability has prompted us to tinker with DPDK besides SR-IOV in the pursuit of a better VOCS. We also look into the optimal disk I/O for Kubernetes with high IOPS applications. Here are the references cited in my presentation. Thank you for your attention. Welcome any comment and question.